I'm going to talk about first passage processes.
Can you use the microphone, please?
Oh, sorry. Yeah, I will. Thank you for reminding me. So, first thing you might want to know is what is a first passage process? I'm just kind of assuming that some of you may know what it is and know it pretty well, but I'm going to make this talk assuming that you don't know what a first passage process is. So first of all, what is it? And so let me give you an example of what it might be. Let's imagine we have some stochastic process which is evolving in time. And let's suppose that our stochastic process is characterized by some variable x. So to make it concrete, let's suppose that x represents how much money I have in my retirement plan. And so here's the money in my retirement plan, and it's maybe going up most of the time with some fluctuations, and then it did something like this. And if my retirement plan reaches this level, I say I'm going to retire. So the question you might want to ask is, how long does it take to reach this level? And the point is that when you first reach this level, that's when you're going to retire. So this point here might be called the first passage time. And so this is a basic characteristic of a first passage process. Now, there's another aspect to this, which is I can imagine going this way in the axis, and it could be that if the amount of money in our retirement plan, and maybe let this represent my total assets, the value of my house, everything that I have, and here it's negative, and if it goes too negative, I might have to go bankrupt. So one could ask the question, if you start at some level, say you start your life with no assets of any kind, what is the probability that you will get to retire, or what is the probability that you're going to go bankrupt? So another version of the first passage process, when you have two different boundaries, is what is the probability that you'll either retire in comfort or you retire in bankruptcy? So that's basically all that a first passage is. So the stochastic process that's evolving, it can be anything, but for the purpose of this talk, I'll normally be thinking just about good old diffusion or good old random walk. And so I want to understand when the random walk first reaches a particular level, and when it reaches that level, how long does it take to reach that level. Now, the crucial thing that determines the dynamics of the first passage is primarily the spatial dimension. So let me just say a little bit about the role of the spatial dimension. So I'll always use the letter little d to denote the spatial dimension. So let's think about the trajectory of a typical random walk that's moving about in free space. So here we are, we start, and we make some kind of a trajectory. And so under time t, will typically be a distance, square root of t away from the origin. And so there is something we can define, an exploration sphere. That's what this guy is. So it's a sphere of radius square root of t, and so its volume is equal to the square root of t to the power of d in d dimensions. And now as the random walk is going for time t, it will visit t sites somewhere in this exploration sphere. So the density of visited points is the total number of points up to time t, which is t by definition, divided by t to the power of d over 2. So this is scaling as t to the 1 minus d over 2. So this is very important result number 1 in this whole story, which is that the density of visited points has a scaling dependence on time. And so what we see is that for d larger than 2, the density is going to 0. And what that means, technically, is that's what's called transient behavior. And what transient means is that as a random walker is exploring the sphere, the density of points is going to 0, so it's very likely that a particular point will never be visited. So, you know, you have your children, they leave home, and they go out in the three-dimensional world, and they never visit home again. There's a good chance that that's happening. For d less than 2, rho is going to infinity. And that means that every point is visited infinitely often in an infinite amount of time. And this regime of behavior is what's called recurrent. So recurrence means that every site inside of this exploration sphere is visited, and in fact it's visited infinitely often. So return for sure means you're going to return infinitely often. So these two basic behaviors are characteristic of first passage processes. So what I'd like to do now is actually derive the first passage probability as a function of the spatial dimension for a pure diffusion process. So let's now compute the first passage probability. So it's done in the notes, and what I'm going to do is give a different derivation, which is much less rigorous and much more sleazy, but it's also the kind of thing that I can write down like just on a little piece of paper, and I can never fail to remember it. So I think it's helpful to show you this derivation because it's useful. So let's try and get a sense of how to calculate the first passage probability. And the basic point here is that there is a simple relation between the first passage probability and the good old occupation probability of diffusion that we're all familiar with, the Gaussian probability distribution. So the idea is the following. Let me write down an equation for the probability of being in position R at time t. So this is nothing more than the good old Gaussian probability of a random walk. But this can be written in a different way in terms of a convolution with the first passage probability. Namely, I can write this as delta of R0, delta of T0, plus the integral from, let's write this. So first of all, I'll write f of R, T prime, T0, T minus T prime, the integral from dt prime, where dt prime goes from 0 up to t. So this is my fundamental equation that governs the dynamics of the first passage probability. So what does this say? The probability of being position R at time t. You could, if it was at t equals 0, you start at the origin, then this is essentially just the initial condition. And notice here, I've been very cavalier about it. I'm talking about continuous space, discrete space, continuous time, discrete time. All that, subtlety just doesn't matter, so I'm not paying much attention to how I'm writing it, and it doesn't really matter. You can do discrete or continuous as you please. This is the crucial equation, or this is the crucial term of this equation. This convolution is represented by the following picture, which is I can write the propagator going from 0, 0 to some point RT. So I'm assuming always that the particle starts at the origin at time equals 0. So this propagator, which I'll represent by a wiggly line, can be represented as dot, which is that I started at the origin, plus the following thing, which is a first passage from 0, 0 to RT prime. So if you're going to go to the restaurant to meet your date at 7 o'clock, you could have gone there at 6:30 for the first time, and then you wander around for half an hour and come back and are there at the appointed time. This wandering around in the remaining half hour, you could have come back to the restaurant once, twice, any number of times. So this propagator factor here is not the first passage propagator, but the good old random walk propagator. So this is the basic equation that describes the relation between the occupation probability and the first passage probability. Now, again, because this is in the form of a convolution, it should scream out to you to do a Laplace transform. And if there's a discrete time, you do a generator function. So now let me take the Laplace transform of all of this. And what you'll get then is P of R and S is equal to delta of R and 0 plus the convolution just turns into the product. F R S P 0 S.
So F is the calculation probability?
F is the first passage probability.
Oh, P is the wiggle.
Yeah, so this is a good old Gaussian. And now we're going to try and calculate F in terms of this Gaussian.
So if you wanted to draw those pictures for more representatively, on the left-hand side of the equal sign, you can actually, you get to that point many times, right?
Correct.
Yeah, you just,
And so this is what's
the same over there. You don't go around once, but many, many times.
Yeah, so that's what the squiggly line is meant to represent here, that I could have, like, if I wanted to do it kind of more perturbatively, I could have done this, and then that, plus this, and then this, and that, and then the sum of all of this is represented by the squiggly line. Yes?
The integral is between 0 and t, right?
Oh, I'm sorry, thank you. Okay. Let's look just at the origin. And for now on and forevermore, I'm always going to deal with the origin. So I'm going to set r equals 0 everywhere. And I'm going to drop the spatial argument. So I only have one argument. So the formulas are less blocky. And so what we're going to find then is f of s, the first passage probability as a function of s. So again, this is the Laplace transform. So I ought to write, squiggle or hat or whatever you like, if I was writing a textbook, and they always have squiggles over transforms. But I hope it'll be clear just by context, so I just don't want to bother writing this. So this is the Laplace transform. And when I solve this equation, I'm going to get 1 minus 1 v of s. So this is important equation number 1. There's a really trivial relation between the first passage probability to the origin and the occupation probability at the origin. Now, the only thing bad about this is written in the Laplace domain, and what we want is everything in the time domain. So I wanted to show you now like this little series of, I would say, sleazy tricks, but they all are correct. And you can't really know that they're correct until you do it right, and then you see that the sleazy approach is actually as right as the correct approach. That allow you to transform this into the time domain. So you find the first passage probability as a function of time. So we want to invert this thing. So first thing, let me write what P of t is. The occupation probability. This is nothing more than 1 over the square root, 1 over 4 pi dt to the power d over 2. We're looking at occupation at the origin, so we don't write the exponential because it's e to the minus 0, which is 1. So that's the exact answer for the occupation probability. So what we want to first do is compute the Laplace transform of this. So let's compute P of s. So it's equal to the integral from 0 to infinity. And for the rest of this discussion, let 4 pi d equals 1. So I'm going to keep writing it. And so I'm going to have e to the minus st, t to the minus d over 2 dt. Now another, yeah.
So this convolution should be from 0 to infinity, right? Convolution only.
No.
Do the Laplace transform. No.
No, I mean exercise for the student. Verify that this equation is correct starting with this. Yeah, it's kosher. Okay, so I want to calculate this integral. And of course, I'm not going to calculate this integral properly. I'm going to do it as easy as possible. And the other thing to say to do this integral easily is that we're typically interested in the long time behavior. And you probably know from Fourier transforms that large x is small k and vice versa. And in the Laplace domain, large time is small s. So we're typically interested in the behavior of this integral for small values of s. And it turns out that there's very different properties whether I'm below 2 dimensions or above 2 dimensions. And in fact, below 2 dimensions is easier than above 2 dimensions. So let's do this separately for the 3 cases. Let's look first of all d equals 1. So in 1 dimension, we have P of s is equal to the integral from 0 to infinity, e to the minus st, 1 over the square root of t, dt. And so when s is small, this thing is going to blow up. When s goes to 0, this whole thing is a divergent integral. And since we're interested in the limit as s is getting very small, the trick that I want to apply is that here we have a divergent integrand, which is cut off exponentially, a smooth exponential cutoff. I'm just going to replace that smooth exponential cutoff by a sharp cutoff at st equals 1. So I'm going to replace this, and so squiggles, 2 squiggles means it's a really not very justified approximation at the level of constants in front, but it's actually asymptotically justified approximation. All right, this is the integral from 0 up to 1 over s, 1 over root t, dt. Now I realize there's yet one other thing I did a little bit unkosher, which is that for a true random walk process, this divergence as t goes to 0 there's no divergence. A random walk, there isn't a blowing up of the probability density. It's just that if you start with a random walk at some point, it's in the long time limit you can make the diffusion approximation. So there's no sense, really, in writing this integral starting at 0. So let me rub out the lower limit and just say some number of order 1, the infrared cutoff in this theory. So anyways, with that caveat, even I can do this integral. This is going like the square root of t, I value 1 over s, so I can get here 1 over the square root of s. So that's the answer in dimension 1. Dimension 2. So at p of s, again, it's an integral. And so now we have 1 over t. So at this stage, you're going to have the integral 1 over s dt over t. So that's log t, and so that's equal to minus log s. And notice that as s goes to 0, they both blow up. D equals 3. D equals 3, we have to work a little bit harder because the integral converges. So the full integral is perfectly well convergent. So let me write now p of s equals this with an undetermined lower limit, integral to infinity e to the minus st, t to the minus 3 halves t. So when s goes to 0, this is perfectly well defined. So p of 0, which is equal to the integral with the undefined lower limit up to t to the 3 halves minus 3 halves dt is less than infinity. So what we do here is say, well, okay, to get the asymptotic correction, so what we see first of all here is that in 1 dimension, 2 dimensions, the string blows up, and that's the deleting behavior. Here, this function goes to finite limit, and what's actually relevant is the first correction to this behavior at s equals 0. So let's, instead of looking at p of s, look at p of 0 minus p of s. It will give us the first correction. And so this is equal to the integral from an undefined lower limit to infinity. So I'm going to have 1 minus e to the minus st, t to the minus 3 halves dt. And now I play the same stunt that I did over here, replacing the exponential by a sharp cutoff. Here I place 1 minus the exponential by sharp cutoff. But here the cutoff function is that this function is close to 0 until st is 1, and then it becomes 1. Because this function starts at 0 and gradually crosses over to 1. And I'm going to replace it by a sharp crossover at st equals 1. So I'm going to write this as an integral from this undefined lower limit up to 1 over s, t to the minus 3 halves. And so this is going to give me t to the minus 1 half, so this is square root of s. So,
The function is 0 up until 1 over
what?
s.
Shouldn't it be 1 over s to infinity?
Oh, I'm sorry, one person at a time.
Function is 0 up to 1 over s.
Correct.
So it should be 1 over s up to.
Oh, I'm sorry. Yeah, I'm sorry, I'm backwards. Thank you. So that's what I'm doing. Thank you. Sorry. So again, this function, this integrand looks like this, and I'm replacing it by that. Okay, so now I've found p of s, and so now I'm just going to calculate f of s, and once I have f of s, I'm going to have to convert it and get f of t, and that'll be the end of the story. So what is f of s? So what we have then is that this is equal to 1 minus p of s, so this is 1 minus the square root of s, and d equals 1. It's equal to 1 plus 1 over log s, and d equals 2, and it's equal to, so where are we here? Yeah, so before we do 3 dimensions, let me just interpret what is this weird thing p of 0 here, because there's something very important. So what we see, first of all, is notice that as s goes to 0, these corrections go away, and f of s at s goes to 0 is equal to 1. So f of 0, of s equals 0, is equal to 1. What does that mean? Remember what f of s is. It's the Laplace transform of the first passage probability. So f of s equals 0 is the same as the integral from 0 to infinity, f of t dt. So this is the probability that you return to the origin at any time. This is the eventual return probability. And let me define this thing to be capital R. And so we see indeed that in 1 and 2 dimensions, that the eventual return probability is 1, which was what we learned was recurrence. If I now go to 3 dimensions, so I have f of s equals 0. Well, according to our formula over there, that's 1 minus 1 over p of 0. So now we have an interpretation of where p of 0 is, because this whole thing is equal to the eventual return probability, which in the case of 3 dimensions is less than 1. And in fact, p of 0 is equal to 1 over 1 minus the return probability. So putting this all together then, I have p of 0, which is 1 minus the return probability. And so I can now plug in p of s is equal to p of 0, which is 1 minus r, minus something which goes like the square root of s. And again, in this formula, there's all those coefficients of order 1 that I have no hope of getting correctly by this approach, but we get the right dependence on time. So if I now plug this into our general formula for the first passage probability, what we're going to find here is return probability plus a correction which scales like the square root of s. So this is for d. So here is now half the problem solved because I have now computed the first passage probability in the Laplace domain. So I'm being a little bit methodological here because I'm trying to illustrate a nice set of tricks that allow you to go between Laplace transform and real-time domain in a very easy and not very technically complicated way. And you see that it's the kind of thing that once you get used to it, and it takes a while to get used to it, then you can do it when you're on the airplane going to a conference and you don't remember how to derive it, and so you can derive it, even you're scrunched into your economy class seat. Okay.
So I think like the complement of this maybe is useful to sort of a complement operation. If you didn't think about first passage time and you try to integrate p of t, there's a distinctive convergence and divergence
Right.
Of that 1 over t to the d over 2, which reflects, if you ask, well, what's the probability after any time to return in less than 2 dimensions,
Right.
that blows up. And that's because you're visiting, your return probability of the origin is more.
Well, the thing is that it is a fact that the return probability is 1, and it's also a fact that the return time is infinite. So even though you return for sure, you have to wait infinitely long to do it. I mean, I don't think it's not evident from P of t itself. One has to look at the first passage probability because, well, let me go a little further and maybe your comment will become more clear. Yes?
Can you comment again on, let's see, the lower limit?
Yes.
Comment again.
So the point is that I start with, say, a random walk. In a long time limit, the random walk will go through a diffusion process. And in the diffusion process, we know that the occupation probability, so if I were doing this at any position x at time t, here would be e to the minus x squared over 4dt. But I cannot use this formula for t equals 0 because it blows up at t equals 0. And that came because I'm using the diffusion approximation to describe the discrete random walk. So what I have to do then when I'm looking at integrals here is that it doesn't make any sense to go to 0 because this formula is incorrect at 0. And so if you want to do it really correctly, you have to write the right formula that's true for all time, not the formula that's true for long time. And since I don't care about what's happening at short time, I just say, well, forget about short time. The contribution from 0 to 1, for example, is some finite number which doesn't affect any of this asymptotics. Okay, so let me now get to the time dependence of the first passage probability. And again, I'm going to do this by a really, what I think is a very handy trick, which is let's write f of s. So this is equal to the Laplace transform, so it's e to the minus st f of t dt. And again, we're interested in the small s limit or the long time limit. So in a long time limit, again, let me replace this exponential cutoff by a sharp cutoff. So I'll write this as very approximately, and I shouldn't write 0 here again. So this is an integral 1 over s f of t dt. But now what is the physical meaning of this formula? So f of t is the probability that you come to the origin for the first time at time t, and the integral of f of t is just the probability that you come to the origin for the first time up to a time 1 over s. So this is nothing more than the trapping probability at time equals 1 over s. So what I mean by trapping probability is, again, imagine that you're a parent, your son and daughter leaves home, and whenever they come back at a particular time, you count what's the probability that they're coming back at time t. And so you wait for like 10 years, and you say, what is the probability that my children have come back? And so what I'm computing by integrating this thing is the probability that they've come back at this particular time. But this thing is equal to 1 minus the survival probability. So what I mean by survival probability is the probability that you don't return to the origin. So the thing about this little trick here is now we have a quantity in the Laplace domain, which is related to a quantity in the time domain, not by doing any integration or anything like that, but just by a simple algebraic relation. So what I then have is that s of t at 1 over s is equal to 1 minus f of s. And so I can now go over here and just write this out. And so I'm going to get, from over there, I have 1 minus square root of s, but now the time is 1 over root s, and so this is equal to 1 over the square root of time, and d equals 1. It's equal to 1 over log t, in d equals 2. And in d equals 3, it's 1 minus the return probability, and then there's plus something which goes like 1 over square root of 2. And now my last step in all of this is that f of t itself, the first passage probability, well, this is nothing more than the derivative with respect to time of the survival probability. The rate at which the survival probability changes is exactly the probability that you come to the origin for the first time at time t. Or if you don't like what I just said, you can just differentiate this formula, and you get s. The s dt is just f. And so from this, I now have my basic result. So let me put it over here. I'm going to get t to the minus 3 halves for d equals 1. It's 1 over t log squared t for d equals 2. And it's equal to constant. Oh, sorry, it's not constant. It's 1 over t to the minus 3 halves for d equals 2. So this is the basic result of the first passage, which is, here's the derivation of the asymptotic behavior of the first passage probability as a function of dimension. So maybe some of you have seen this t to the minus 3 halves for one-dimensional diffusion, and this is where it comes from. I'm actually going to show an independent way of deriving the same result in just a minute.
So it's curious that the 1 and 3-dimensional asymptotic power law is the same if the amplitudes are equal.
Well, yeah, the amplitude.
Excuse me,
the other point here is it's better to sort of compare over here because the survival probability has the same asymptotics, but this thing is going to 0. This thing is going to a finite limit. This finite limit is what's really important.
Could you repeat the question?
Oh, the question was, it's kind of curious that it's the same power law in 1 and 3 dimensions. Yes?
So in those expressions you wrote down, on the right-hand side, can t be anything, or is it still t equals 1 over s?
Yeah, so I'm using the substitution t equals 1 over s to go from the Laplace domain to the time domain without doing any integration.
Yeah, it's any function of t. It's not
Okay, so on the right it's any... Oh, okay.
Yeah, I mean, it's one of those things that you have to, like, check for yourself to really feel you believe it. I mean, because it's like, some of this may seem like black magic or bullshit, depending on your perspective, but you really have to check it by doing, like, integrations carefully and then realize that what I'm doing here is entirely justified.
Good. So in an equals 3 case, does it approach the value from below, or is it in the negative?
I've been cavalier with the signs, but I know that what I've written here has the correct sign. The point is that, you know, the survival probability decays to a finite value, and so this has to be positive correction. And I mean, the signs are correct. It's just I've not paid attention in the intermediate steps. Yes, Royce.
in addition to saying that it can be done in a kosher way in getting the
Yes.
answers, you could just say it's dimensional analysis. T is 1 over S.
Yes, that's true. So the question was, can't you just do this by dimensional analysis? T is 1 over S.
And that, of course, depends on scaling variance.
Right.
And so on. So once you get a scaling, then you can do it.
Okay. All right. Let me now go to two basic characteristics of first passage processes, which are the so-called exit probability and exit time. So let's look at exit probability and exit time. And let me derive this in the framework of a one-dimensional example, but in fact, the derivation is true in an arbitrary domain. Once I write down the answer for one dimension, I'll just write the generalization in an arbitrary sense. So let me put it in the following framework. Let's suppose we have an interval, 0L. I start with a random walk somewhere in this interval. And so here we have a random walker, and say are there mazes around here? Leo? Mazes. The geographical mazes.
Oh, yeah.
There are. Well, no, okay. I mean, because in Los Alamos, there's mazes everywhere. So let's imagine that this is actually a geographical thing which looks something like this. So, there's a cliff here, there's a cliff here. You put a random walker on this one-dimensional mesa, and if he hits the edge of the cliff, he dies. And you can ask the following, but maybe actually do it even better here, which is, let's suppose that on this side there's a little. Let's say he dies in either end. So the question we might ask ourselves is, what is the probability that the random walker is going to fall to his death on this side or fall to his death on this side? And also, how long does it take before he dies? And so that's what's characterized by the exit probability, or the death probability, and the exit time. So let's first of all compute the exit probability. Now, before I do that, there's another interesting philosophical point which is coming up, which is that diffusion is more complex than electrostatics. But as we're going to see, this question of the exit probability, this means the probability of exiting at any time. The way that you would do it from the perspective of diffusion is that you'd say, well, I solved the diffusion equation in this one-dimensional interval, compute the flux out of this side and the flux out of that side, I integrate over all time, and I would then compute the exit probability. That would be the formal way of doing so. So you take the time-dependent diffusion equation, solve for all the time dependence, and then integrate over all time. That time-integrated property actually comes as a solution of an electrostatic problem. Because if you take the diffusion equation and integrate over all time, you just get electrostatics. So this fundamental relationship between electrostatics and diffusion turns out to make a lot of these first passage processes very pleasant and very familiar. So first of all, let's compute the exit probability. So let me define E sub n as the probability of, say, death at x equals L when starting at n. So I start at some point n here, and so half the time it hops to the right, half the time it hops to the left, and I want to ask, what is this death probability? And so there's a big simple recursion formula that this death probability obeys, which is the following. So I just look one step into the future. So in one step into the future, I've either done this, or I've done that. But if I've done this, then at this point, there's a death probability from this point. And so all I have to do to compute the death probability from n is to say, well, 1/2 the time, I made a step to the left, and then I have death probability from n minus 1. And 1/2 of the time, I step to the right, and I have death probability of n plus 1. And this equation is nothing more than just the discrete Laplace equation in one dimension. You can probably recognize this as the discrete second difference. And so in the continuum limit, this just becomes E double prime is equal to 0. And we're doing this with the following boundary condition, that we want that we're looking for death at x equals L. So that means that E of L, I guess I should put this as a subscript here, E of L. If I start at the right edge, then I die at the right edge. If I start at the left edge, then there's no chance I'm going to die at the right edge because I'm dying at the left edge. So we have this. So the equation we want to solve is just the Laplace equation with these boundary conditions. And so for this particular case, this E as a function of n is nothing more than n over L as a solution to this simple problem. More generally, we can do the following thing, which is, so here's a more general framework. So let's suppose instead of having like some very specific domain, we have just some arbitrary domain. So here's my domain D. And there's a boundary. So here's the boundary. So boundary B. And typically, the kind of situation one might be interested in is, for example, divide the domain boundary into two pieces. Say one half and another half. And I might be interested in what's the probability, if I start with a random walker at some point here, that he's going to exit the domain over here in the purple part or in the white part. And so for this problem, what I want to solve then is Laplacian of the exit probability is equal to 0 with the exit probability. And so let's call this part of the boundary B plus, the plus part, and here let's call this B minus. And so, for example, if I want to ask what is the probability that the particle exits out of B plus, then we have to solve the diffusion of the Laplace equation with the boundary conditions that the exit probability out of B plus is equal to 1, the exit probability out of B minus is equal to 6. So this is a simple electrostatic problem. And so the point is that for various sorts of simple geometries that you've all worked out in your Jackson graduate electrodynamics class, you can now solve first passage problems in a very simple way. So let me give you one concrete example of this, which is, let's suppose we have a sphere of radius A in 3 dimensions. And I put a particle a distance r away from the origin. So we now have learned that in 3 dimensions, if I put a particle some distance away from a finite sphere, there's only a finite chance, less than 1, that I'm going to go back to the sphere. There's a better chance I'm going to wander off to infinity. What is the probability that I'm going to hit the sphere of radius A? So what do we do to solve this problem? We write Laplacian of E is equal to 0. And for the sphere, well, if we want to ask the probability it's going to hit the sphere, we want to solve with the boundary condition E at r equals A is equal to 1, because if I start on the surface of the sphere, then I've obviously hit it. And the boundary condition at infinity, well, in fact, in this case, you don't have to really pay attention to it because, well, we'll see. I'm not sure I have a good explanation of how to ignore the boundary condition at infinity, but I'm just going to ignore it. So here, the solution is A over R. That is the solution to the Laplace equation in 3 dimensions, 1 over r potential, and that satisfies, that obeys this boundary condition. So that's the answer. So this is the probability that if you start a distance r away from a sphere of radius A, that you'll hit it, A over r. So you've solved it. This is a very non-trivial first passage problem if you want to solve it. We're solving the full time-dependent diffusion equations, but it's very simple here.
Can you repeat again how you formally would set up the problem?
Yeah, so what I would do if I was just, if I didn't know anything, I'd say I would solve dc dt is equal to d Laplacian of c on some domain. Then you would compute the current J, which is equal to d dc, like gradient of c. Then you would integrate, over all time. And the exit probability would be nothing more than the integral of j dt equals 0 to infinity. So here I'm saying compute the current to some part of the boundary. So I'd have to, like here, if I just have 2 points, I'd be just computing the flux at a given point. then if I have a continuous boundary, I'd have to do the integral of this over the boundary itself, and then I integrate over all.
It's a total amount of probability fluid that flows out.
Exactly so.
So there are situations when some of it remains within the boundary.
Well, not if the domain is bounded. If the domain is infinite, then there might be some that never hits, and I may say something about that. But yeah, for example, here there's some chance that some of the probability doesn't hit the sphere.
But for this, doing it this way, you would take a delta function of n or something like that.
Yeah. So the thing is that I have to
What's
solve.
the initial boundary condition?
No, so the initial. Okay. So this is still not completely well posed. I'd have to have initial conditions, which is that C of R t equals 0, for example, is equal to delta of R minus R naught. That starts somewhere. And some boundary conditions. Boundary conditions would be that C on the boundary is equal to 0, for example. And then it's a well-posed problem. Let me now talk about the exit time itself. So we start with our one-dimensional random walker on this mesa. How long does he have to live before he's going to fall off the mesa? And again, using the same kind of formalism, one can write the following recursion formula for what's called Tn is the time, exit time, starting from n.
So when you say probability of falling off, you apply over all time in defining Tn.
That's right. This is the probability that you're going to fall off at any time. The eventual exit probability. Eventually, the random walker will fall off. You just want to know what is the total probability of falling off on the right side, the total probability of falling off on the left side.
So you can't really use
What?
In principle, you can probably use.
Well, no, this result was for just free diffusion and looking at the approach to single points. This was only for free diffusion. Now we're looking at problem boundaries.
But if you script E the same as the capital E,
Is my script E
E sub n,
same as,
what's the relation to capital E?
where's my
Go
capital? Here. Oh, yes.
You're trying to identify.
Yeah, that's the same. Same thing. Yes.
So in that the 3D Coulomb case, is the 1 minus E case the thing just diffusing around infinite?
That's right. So 1 minus this, 1 minus A over R is the probability that the random walker wanders around forever and never returns home to his mom and daddy.
So that happens only in 3 dimensions, is that right?
Well, in arbitrary dimension, shall I tell the answer in arbitrary dimension? D minus 2 power.
Right.
So that's all that happens in arbitrary dimension. As long as the dimension is larger than 2.
Can you still use this result and integrate over the boundary and over time and reproduce?
Well, the only thing is I'd have to solve this. All of this is based for free diffusion. So if I wanted to solve for some boundary, I'd have to first write the probability being at the origin in the presence of those boundaries, and then go through this whole rigmarole to then extract f of s and then invert it in time. But that's not a recommended way of doing it. All right, let's now go to the exit time starting at n. Yes?
Just a quick comment on that. This sort of shows how remarkable diffusion is, that you get a whole kind of extra power, right? Like, so if you have a walk in a random direction but in a straight line, you would expect it to sort of go as the surface area, right? So you expect something that goes like...
When you say it goes, what goes as the surface area?
The chance that you would hit the sphere. Right?
Ah.
It's sort of related to the surface.
Yes.
And because you're diffusing instead of just going in straight lines, you sort of get this whole extra power of R.
Okay, that's a very good comment, and in fact, that's the next thing I'm going to come to. So I'm going to sharpen that comment a lot because that's really an amazing feature about diffusion that is worth spending some time on. So let me just first do the exit time problem because it follows very simply from this exit probability approach. So what is the time that it takes to exit? So I start here at position n, and so I might step to the right, and I'm at a new point, and then I've wasted 1 unit of time in getting here, and then I have an exit time from this point. Or I could have stepped one step this way, and I've wasted 1 time unit, and then I have the time from another point. So I argue that the recursion formula is Tn, so 1/2 of the time, I step, say, to the left, and I wasted a time delta t in doing that. So delta t is my time unit. And 1/2 of the time, I step to the right plus delta t. And so the equation that we get then is Tn. So again, you see that this plus this plus this is nothing more than a discrete second derivative. Then I have a half plus a half delta t. So I get back the same equation. So now let me go immediately to the continuum limit. Right, this is t double prime is equal to minus 1. So that's the equation that happens here. So how did delta t turn to minus 1? Because if I imagine doing the continuum limit, there's a delta x here if I expand this in a Taylor series, and when I do the second derivative, there's a delta x squared. So delta t over delta x squared is the diffusion coefficient, is 1 over the diffusion coefficient, which I've just said equals 1. So the problem that I want to solve then is the second derivative is equal to 1, with t at 0 equal t of L is equal to 1. So if I start at the boundary, then I'm already there. It doesn't take any time to get to the boundary. And so this problem also you can solve very easily, and the answer for this is t of x is equal to x L minus x over 2. And I'll leave you to ponder the consequences of this very simple result.
Now, if you wanted to have anisotropic bias diffusion,
Absolutely.
that can still be done.
Absolutely. I mean, so in fact, instead of putting here 1/2, I could have put p and q, and then you go through the same old rigmarole, and what happens here, it would be plus v t prime is equal to minus 1. So, yes. So all this works for arbitrary hopping processes, and when you can take the appropriate continuum limit. Okay, wow, time is flying here. So there's two more things that I'd like to discuss. And so the first one is related to Meredith's comments about this feature of this weird power dimension in diffusion. And so let's now talk about the reaction rate. So in chemical kinetics, a very basic quantity which appears over and over again is the notion of the reaction rate. And so let me define what this reaction rate is. So let's imagine that we have an absorbing sphere of some radius a. We have a gas of diffusing particles outside, so these guys are just diffusing. And when they hit the sphere, they're absorbed. And the question we want to ask is, what is the absorption rate? This absorption rate I'll define as the rate constant K. And the question is, what is the absorption rate? So first of all, let me tell you the result that Meredith mentioned, which is really quite amazing, is that if instead of having diffusing particles, you had a collimated beam of light, and said, what is the cross-section, the collision cross-section of the sphere to the beam of light? The collision cross-section would clearly be proportional to the cross-sectional area. It would go like a squared. What's amazing about diffusion is that the analog of the collision cross-section is this absorption rate. And in 3 dimensions, let me tell you what the answer is. It's equal to 4 pi d times area to the power 1. So, at first sight, it just seems like crazy.
Radius.
Right, radius.
Not
That's right. It's radius. Radius to the power 1. Yeah. So, that's amazing about this. You say, how can it possibly be only going like the first power of the radius instead of the second power of the radius? So, maybe put an exclamation point here. So that's what happens in d equals 3. So what I want to show you is how you calculate this absorption rate. So let's do the calculation. So let me first of all set the problem up in a maybe more kosher way. So what we want to do here is we want to solve the c dt is equal to d of paucity of c with the initial condition, for example, that I have a uniform gas of particles initially. So initially, let's say that C R and T equals 0 is equal to 1 outside the sphere. And I have an absorbing boundary condition, C at R equals A at any time greater than 0 is equal to 0. So that's the problem that I want to solve. Now, it turns out that there's two very different behaviors for this reaction rate depending on whether I'm above 2 dimensions or 2 dimensions and below. As I've just presented earlier, 2 dimensions and below, random walks are recurrent. And so if I just kind of look qualitatively at what you might expect the concentration of particles to look like as a function of time, so for d less than 2, what I might expect is the following. So here's the function of r, here is CR as a function of time. And here's the radius A. So we start initially with this step function. We'll do something like this. And it continues to coarsen with time because particles are certain to get trapped by this absorber. And so there's a depletion layer whose radius scales like the square root of dt. And so the system never reaches a steady state. And because the system never reaches a steady state, there's no notion of a steady state absorption rate. You see that the slope is getting smaller and smaller with time. The slope is proportional to the local current, and so the trapping rate is going to decrease with time. D less than or equal to 2. For D strictly larger than 2, well, we know what the answer is. If I plot CR as a function of T, we start off again like that. But in a long time limit, because random walks are transient rather than recurrent, we will eventually reach a steady state. And so what's a steady state solution? Silence. If I forget about this guy, what equation is this? Laplace equation. What is the solution of Laplace equation in d dimensions?
Well, right, d minus 2.
There you go. Okay. So let's now do this problem. So first of all, let's talk about the case d equals 3. Let's do general. Let's do d larger than 2, strictly larger than 2. So I want to now calculate this absorption rate. So what I would say is that in the long time limit, C of r t going to infinity is equal to a over r to the d minus 2 power. So the flux, which is equal to dc by dr, and so now I'm going to forget about constants. I'm going to have a to the d minus 2 power here, r to the d minus 1 power. And the total flux, the total absorption rate then is going to be the spatial integral over the surface of the sphere. Somebody write it sort of like electrostatics, j dot ds. It's the integral of the current over the surface of the sphere. But notice that the current is a to the d minus 2 over r to the d minus 1. The surface area is r to the d minus 1, so the r's cancel. I'm going to get a to the d minus 2 power. And j itself, I've got a diffusion coefficient. And so we see that what we're going to get here is something which scales as the diffusion coefficient times a to the d minus 2 power. So in 3 dimensions, it's linearly proportional to the radius. Another crazy thing about this is you see that when d is 2 or less, that in fact, the bigger my absorber, the smaller the absorption rate. It's going backwards. It's something crazy is happening. So this result is only correct for d strictly larger than 2. And for d less than 2, something else is happening. And what else is happening here is the fact that the flux is going to 0 as a function of time. There's no longer any steady state. And I can no longer do a steady state calculation to calculate the reaction rate.
You see that you diffuse gradient over there because it puts on the d minus 3, which vanishes into
Exactly, yes.
So for t greater than 2, what's the profile C of r of t?
So it's falling off as a power law, like something like that.
That's the steady state.
Correct, that's a steady state.
So is the two-dimensional case special, or is it?
Yes, 2 dimensions is very special, and the reason it's special because it's right at the boundary between, really recurrent, where the density of points visited is diverging as a power law time, and transient, where the density of points is going through constant value. Right at that boundary, 2-dimensional diffusion is very delicate, and so one always gets logarithmic corrections that characterize things like the reaction rate, things of that nature.
Sid,
Yes.
could you force the 1 or 2D problem to reach a steady state by putting a source at infinity?
Sure, we can do that.
You just don't.
Well, I mean,
You just want to look at the transient problem.
yeah, I'm looking here. I'm looking at the classical problem of just the transient problem that I begin with some initial state. But you're absolutely correct. I could have a source at infinity, and then there would be a steady state in one dimension or two dimensions. But it's not relevant for this particular case. Okay, so what I'd like to do, let's see, what should I do now? What happens then for d less than 2? Let me just mention very briefly something here, because I want to introduce to you an approximation which I have found in my experience is like the most useful thing that I ever learned in diffusion. And it allowed me to solve complicated diffusion problems kind of like, again, back of the envelope. So let's do the same problem in d less than 2 dimensions. And so the idea of what happens in less than 2 dimensions is the following basic observation. Let's imagine looking at some late time. So our diffusion field looks something like this. It is perturbed by the boundary up to a distance root dt. But if we're much further away than root dt, we don't know that there is a sucking vortex here that's going to suck all my particles in. So there's a sort of boundary layer. Outside the boundary layer, the system is basically static. Inside the boundary layer, well, it's only extending out the range of root dt, and the system has plenty of time. A random walker at a time t will typically explore a region of the order of root dt, and so inside of this boundary layer region, the system is almost static. And so this motivates something known as the quasi-static approximation. And so the quasi-static approximation is basically to say, well, here is a complicated diffusion problem. And if, as an exercise for the student, if you really want to be a masochist, solve the diffusion equation with this initial condition, this boundary condition in less than 2 dimensions. And you'll find you can solve it, and if you want to even find, I even know where you can find the solution written down in the book, but it involves Bessel functions. It's a big mess. You'll have to remember all your Bessel function technology. It can be done, and so it's exercise for the student. But if you want to calculate the effective absorption rate, then you don't have to do a lot of that stuff. You don't have to work quite so hard. And the idea of the quasi-static approximation is we're going to do, instead of solving the full problem, we're going to solve the following problem. Instead, solve the following thing. We're going to solve, quasi-static means that inside its boundary layer, the system is effectively not changing very rapidly. So we're going to just solve Laplacian of c is equal to 0, which is a lot simpler equation to solve. But to make this a well-defined problem, we need to have c at r equals a and t greater than 0 equals 0, the absorbing boundary condition. To make this well posed, we need a second boundary condition on the other side. And the second boundary condition will be c at r equals the square root of dt at time t is equal to 1. So all I'm saying here is that outside in this far zone, the system doesn't know that there is a sucking vortex over here. Somewhere around root dt is where the first glimmers that there's something bad happening here that's trapping off particles exists. So we're just going to match the static solution to, the static solution to the Laplacian solution inside of the boundary layer zone. And because this is kind of a self-inconsistent approximation, morally, even though it's mathematically self-consistent, so we use the word quasi-static approximation, because we're solving a static equation with a moving boundary condition. And that's where it's called quasi-static, because it's almost static, but not quite.
But I mean, I think you maybe misspoke, but outside of root dt, it's static.
It's static.
Inside is dynamic. You're just calling that region 0. That's
Well,
where
it's
it's
dynamic, but the point is that inside of this dynamic region, a random walker has essentially explored this region thoroughly. So the system has a chance to come to a local equilibrium inside of the cell. And so that's why we can write a static equation, even though the system is not static. So, there's this notion that things are happening that the profile inside of here is not changing very much as a function of time. So we can replace it by a static equation, and we're going to get the time dependence by this effective time-dependent boundary condition. So let me now solve this problem. Let's just do the case of d less than 2. D equal to 2 is equally simple, but it's just that you have logarithms and it just takes a little bit more time to write it out. So we want to solve then the problem c double prime plus d minus 1 over r, c prime is equal to 0. That's the diffusion equation. And so from elementary differential equations, you see that there's 2 powers of r downstairs everywhere. The solution is power law. You plug in a power law, and the solution of c is equal to a plus b r to the d minus 2 power. Now let me implement the boundary condition. So let's call this 1. Let's call this equation 2. So 1 would tell me c of r is equal to, so it's actually easier just to write down the equation without deriving anything. There's like obvious at the end that's correct. Let me write this as b times r to the d minus 2 minus a to the d minus 2. Right? This obviously satisfies the boundary condition. It vanishes if r equals a. And then to satisfy 2, I want that at, I'll write, so now here's the final answer. This is going to be r to the d minus 2 power minus a to the d minus 2 power. I want it to be 1 at r equals root dt. So put here root dt to the power d over 2 minus a to the d over 2 power. And then you see manifestly that when r is equal to root dt, this is manifestly 1. So this is the solution. So a nice feature about this quasi-static approach is that it doesn't take any work to solve this problem. And so now we can do the same...
Excuse me, question.
Please.
For the second boundary condition, is there any restriction for the time?
Is there what?
Is there any restriction for the time? Restriction.
Restriction on what?
For time.
No. Any time positive. I mean, this is meant to be appropriate for the long-term limit.
The first term, if x squared dt equal a, then the second boundary condition is contradictory with the first condition.
No, I mean, we're thinking of, I mean, typically, okay, you ask for restrictions. So let me say that the appropriate restriction is time is large.
Okay.
Let's just look at the large time varies.
So that's when things don't vary very rapidly, right? And
Correct.
Initially, you go from step function to a smooth function, so that's a very rapid change.
Yes, but in the long time limit, this is a very smoothly varying profile that's only changing slowly with time.
So it's changing slowly with time everywhere, not just outside, but even inside the boundary layer.
That's right.
That's your justification.
Correct. Okay, and so the same approach will work for 2 dimensions, and now we can go through the same exercise of solving for the flux, integrating it over the surface of the sphere, and we can calculate the reaction rate both above 2 dimensions and below 2 dimensions. So let me now just quote what the result is that A asymptotically scales as b a to the d minus 2 power for d larger than 2. For d less than 2, it scales as, by the way, I think that formula 345 in my notes is incorrect, and this is definitely correct. So we have here 1 over dt to the power 1 minus d over 2, and it's 1 over log t, and d equals 2. I actually do have one other thing I'd like to present, but I just don't want to take too much time. So organizers, advise me: should I stop here, or can I say one more thing? Okay. So I'd like to show you one example that I find really a lot of fun, and it's a bit idiosyncratic, but I hope you'll also find it a little bit amusing. And that's a question now of, let's look at survival of multiple random walkers that like to kill each other when they meet. So let's study the following problem. Suppose that I have 2 random walkers in line. Here's one at x1, here's one at x2, and they diffuse. So let's imagine that this is now space, and here's time. And so they diffuse around something like this. And if they meet, they just kill each other off. And we can ask, what is the survival probability of the function of time?
So you're saying they both die in this event?
They both die in this event.
Okay.
What is the survival probability? In fact, we already know what the answer to this is, because what we can do to solve this problem is that we can go into a reference frame fixed with respect to x1, and then the separation between these two particles is doing a diffusion with a diffusion coefficient twice that of the particles themselves. So we now have a fixed boundary, and this distance is diffusing, and we ask, what's the probability that this boundary stays a positive distance away from the origin? And the answer to that problem is what I just erased here. It actually is t to the minus 1/2, survival probability of a one-dimensional random walk with an absorbed boundary. So that's not very interesting, or maybe it is depending on your taste. But now let me do the following thing. Let's suppose I put a third particle here, and let's now imagine that we call our particle in the middle, let's call this guy a lamb, and this guy is a lion. This guy is a lion. And the two lions, they're not going to bug each other. They're just searching for lambs to eat. We can ask, what is the survival probability of the lamb? And so I want to show like a nice construction that allows you to solve everything in a very nice way. So I want to ask, what is the lamb's survival probability as a function of time? And in fact, there's actually two different problems that you can define here. One is when the lamb is in the middle, it's surrounded by the lions. That sounds pretty bad, actually. And the other one is when the lamb is on the far side of the lions, and that maybe seems like it has a better chance of surviving. And in fact, those two problems have different survival probabilities, and I'll show you how to calculate them right now. So how do we do this? And it turns out that the right way to think about this problem, or a useful way of thinking about this problem, is instead of thinking of 3 random walkers in a line. And so I'm assuming here that my lines are infinitely stupid. They're just diffusing around, and if they come upon a lamb, they're going to eat it, so they have no sense of smell. And the lamb is also infinitely stupid. It sees a lion, it just diffuses randomly. But in fact, the problem with you put any intelligence on these agents is still unsolved. So if you really want to have an interesting unsolved problem, give these guys some intelligence, and you'll see very quickly this problem is extremely hard to solve. But what I'm going to do here is that for purely diffusing particles, we have x1, x2, x3, and they have to satisfy this constraint. So instead of thinking of a random walk in 3 random walkers in 1 dimension, think of 1 random walker in 3 dimensions that has to satisfy the constraints that x1, x2, and x3 are constrained in some way. So let's talk about this particular problem here. So we want x2 bigger than x1, and x3 bigger than x2. So the plane x2 equals x1 is this guy. And we want it to be x2 is bigger than x1, so we have to write here. And then the plane x3 bigger than x2, so that's the plane coming out of the blackboard this way, and I've had some practice in doing these plots, so I know how to do it without getting screwed up. So that's the other plane. This is the plane 2 equals 3, and we want to be on this side of the red plane, and we want to be on the back side of the white plane. And notice that they meet along this line 1, 1, 1, 1, 1 here. And so the problem is that we want to survive, the lamb has to be inside this wedge-shaped region of some opening angle theta. And so, in fact, this is the end of the solution to this problem, because what we've done now is we've transformed from 3 random walkers in a line to the survival probability of a random walker in a wedge-shaped region of some opening angle theta. Now, I've actually gone on a little bit too long, so I was going to show you how to actually derive this without derivation, because there exists a way of deriving the survival probability in the wedge-shaped region of opening angle theta. So if you want to see me do it, ask me after in the break or something like that, and I'll be glad to do it. But it turns out the survival probability behaves as t to the minus pi divided by 2 theta. And the other part of this problem, which is non-trivial, is what is this opening angle? And if you stare at this for a second, you can, or even for an hour, you can drive yourself crazy. But here's a trivial way to figure out what the opening angle is, which is, let me just do this other plane, x1, x3. Let me just draw it, just for the hell of it. And if you draw that other plane, it looks something like this. And then you see that there's 6-fold symmetry here. So this angle here is 60 degrees. So the survival probability of a lamb which is stuck between two lines is t to the minus 3 halves. If you do the lamb on one side, the survival probability is t to the minus 3/4. So there's all kinds of amusing survival probability problems that you can define in terms of mapping one-dimensional problems into these higher dimensional problems, and ultimately they boil down to diffusion in an absorbing wedge-shaped region, which is a beautiful problem in its own right. And I hope I've just given you just a little taste of how interesting some of these problems are and how deep they are, and also that there's some very powerful techniques available to solve them. But if you want now an unsolved problem, 3 is easy to solve, 4 is unsolved. Want to be famous? Solve the 4-particle problem. I'm done. Thank you.
All right, questions?
So I was wondering, so the asymptotic behavior would probably not depend on the details of the distribution we start with of the random walker as long as it's symmetrical, right? However, how about fat-tail distribution?
Okay, well, now, I mean, if you're going to put fat-tail distributions, and all of this goes out the window. So for a fat-tail distribution, the calculation of first passage probability has been done, and it depends on the exponent associated with the fat-tail of the single-step hopping probability. Yeah. Okay, yes, please.
So I was a little confused when you said that this reaction rate problem didn't have a steady state solution.
Below in 2 dimensions and below.
Yeah. Do you mean there's no non-trivial solution? Because 0 obviously works.
Yeah, but the thing is, if you start with an infinite domain, then you have to wait an infinite amount of time before you get to that static solution.
Yeah, but you usually have to wait an infinite amount of time to get to a steady state solution.
Yeah, okay, but...
Okay.
Touche. Yes.
A comment just on your reaction rate stuff.
Yes.
It's kind of an amusing application because you can use it to calculate how big an organism has to be and before it has to start swimming. So you just showed that like the reaction rate, if you just wanted to be a sphere and sit there and wait for all your food and oxygen to come to you, scales as A.
Right.
How many nutrients you need, scales as A cubed, and you can estimate that number. When A is really small, A cubed is much smaller than A, so
right.
there's no need to swim. You can just sit and get everything you need from the environment. But as
that's
you start
really
getting
cool.
big, there's a point where you won't be able to get all your oxygen if you just sit there and wait for diffusion, and you have to start swimming. And you can do that estimate, and you basically get the answer of like a few microns above which.
Oh, that's fantastic.
Has to start swimming around.
That's really fantastic.
So that's a cute application for me.
That's really nice. That's really nice. By the way, one other thing just in this whole story of the reaction rate is that if some of you noticed there was some electrostatics being snuck in here, for the good old reaction rate about 2 dimensions, what I basically was doing is calculating the capacitance of a sphere. So if you take your favorite electrostatic problem and compute the capacitance of the object, it's the same as the reaction rate to that object. So you can now do ellipsoids or disks or sticks, and you can find the reaction rate of all these objects. And anyways, it's just an interesting sci-fi. Yes, please.
In the reaction rate field, if you add some interaction between the random walkers, for example, hardcore interaction, is in asymptotic stay the same, or?
I guess what I would say is this is a problem that's not really been very well studied. I know that there was a recent work by Yannick Kondev and 2 collaborators where they were interested in the reaction rate inside of a cell, so they had a crowded environment. And they did some kind of a self-consistent approach to try and estimate the reaction rate in crowded environments. But I have to admit, I don't know what the result is. But the thing is that I think you've asked a really good question, because in the framework of biological applications, you have diffusion in crowded environments and there's interactions. And so to develop a good analytical approach to such a problem, I think is still not been done.
Any other questions?
Yeah.
Just to comment on the last one, I mean, at least naively, if you think of like polymers with self-avoidance, and make some contact connection to or analogy with the diffusion and interaction, I would think that it changes the exponents, and since a lot of this depends on that it's t to the 1/2,
Right.
that it would modify it to some.
Oh, absolutely. I mean, the excluded volume constraint means that then the random walk trajectory or the self-avoiding walk trajectory is very much expanded,
Right.
and so it shifts all of this line of argumentation, absolutely.
Any other questions? Well, if not, then thanks everybody.
Just give this to